Hi everyone, in this video we're going to continue with trying to graph polynomial functions by hand, and we are just going to add one little bit of trickiness to this. We're going to talk about multiplicity of zeros. So basically what happens is if you factor a polynomial and one of your factors has a power on the entire thing, that's still an x-intercept, but it changes the behavior of the graph near the x-intercept. So let's just start as usual and try and get these things in factored form. This one, let me think. I'm going to factor out a -2 first. Again, if you don't spot that right away, you can factor it out later, but I think it's slightly easier if you factor it out first. So I'll get an x cubed plus 2x squared minus 4x minus 8. Since that was a -2 I factored out, it will switch all of the signs. Is this thing going blurry again? Here. Let's see if I can get it to focus. Okay. There we go. Okay, so now I'm going to go ahead inside the parentheses and create two groups. So from the first group, I can factor out an x squared, and I'm left with an x plus 2. From the last group, I can factor out a -4, and it does have to be a -4 that you're factoring out. So it'll switch to an x plus 2. Again, remember, if you're ever unsure, you can distribute in to check yourself. This will give us a -4x minus 8, so that's looking perfect. Now, inside the parentheses, I have a difference between term 1 and term 2, and both terms contain that common factor x plus 2. So I'm going to go ahead and factor that out. So I have the -2 still sitting out in front. I now have an x plus 2. And then I'm left with an x squared minus 4. So there's my x squared and my 4 left over when I divide out the x plus 2. If you'd like to keep this set of parentheses, you can. It would just be around the entire thing. At this point, it doesn't have any extra meaning. It just means multiply, and just having a single set of parentheses already means that. So I'm going to leave it off. Okay, so I'm ending up with -2 times x plus 2, and then the x squared minus 4 factors into an x plus 2 x minus 2. So I actually end up with an x plus 2 squared x minus 2. Since I had two factors of x plus 2, I get that squared. Now that I have it in factored form, I can say where my zeros are. My zeros are at -2. This one is going to be interesting because it has multiplicity 2. So all I'm saying when I spot that is that it has a power of 2 on it. And I'll talk about what that means on the graph in a minute. So recognizing when you have a power on one of these factors is really important. And then we'll talk about what exactly it means. We also have a 0 at 2, 0, and that's multiplicity 1. So multiplicity 1 is going to be just like what we looked at in previous examples. Is this going blurry again? Okay, I don't know what's up with my camera today. Here, maybe I'll put more lights on and see if that helps. Okay, so multiplicity 1 is just like what we looked at in the previous video. When you cross through an intercept with multiplicity 1, your graph should just head straight through. It could be headed up or it could be headed down. It could be more steep or less steep, but it should just cross straight through. So if you zoom in on an intercept of multiplicity 1 far enough, it should basically just look like a straight line where it crosses through. If you have a multiplicity of 2, what happens is if we plug in -2, it makes this 0. If we plug in something a little, let's think, a little smaller than -2, like -2.5, this is going to give us a negative number, but then when we square it, it actually becomes positive again. If we plug in something a little bigger than -2, say -1.5, this is a positive number. When we square it, it's still positive. This is very different from here. If we plug in something a little bigger than 2, this whole factor comes out positive, whereas if we plug in something a little smaller than 2, it comes out negative. So for a multiplicity 1, in fact for any odd multiplicity, this factor will change from positive to negative at the intercept, and that will mean that we've crossed through the axis. When there's a square on there, you don't actually cross through because this factor doesn't change signs. The negative gets eliminated by the square. So what will happen is we'll have a bounce. Whenever there's multiplicity 2, there's a bounce. And you'll have to use your global behavior to figure out which direction. There's no rule about it being above or below the axis, but it will definitely bounce off, whereas multiplicity 1 will definitely cross through. We also need our global behavior. The form we started off in gives us that for free. Remember, I put all these in descending order for powers, but even if they're not, it doesn't matter what order they're in. It's all about finding the highest power. So my global behavior is going to be a y equals negative x cubed. I don't care if you write the 2 in there, it's fine. I'm just trying to emphasize the fact that what I care about is the power, even or odd, and whether it's right side up or upside down. So now I'm picturing an upside down cube, which means my arrows are going to go down on the right side and up on the left side. So when I put this together, I need to cross at 2 and negative 2. Okay, so let's see. I'm coming from positive infinity. When I get to the 0 at negative 2, I'm not going to cross through. I'm going to bounce off the axis. And then when I get to the 0 at 2, it's multiplicity 1, so I am going to cross through and then just continue to negative infinity. And my arrows look great, pointed up to the left and down to the right. So again, this is really a rough sketch. It's probably a little too rounded out, but that is the basic shape of this one. So if you have a second power on the factor that gave you your 0, bounce off the axis. Signs will not change. You'll either stay above or below. Okay, second one, we have to do the factoring again. So I actually have a more substantial greatest common factor here. I can factor out a 3 and an x cubed, so I'm going to do that first. I'm left with an x squared minus, divided by 3, 6x plus 8. And that looks factorable as well. So a 3x cubed times x. And it should be a minus 4 minus 2. So my zeros are at 0, 0 from this first factor. Don't forget about this one. If you factor out an x cubed, you have to make sure you set this whole thing 3x cubed equal to 0, which will happen if x is 0. I also have one at 4, 0 and at 2, 0. My global behavior is determined by the fifth power term. So this is going to be right side up, x to the fifth. Again, if you want to write the 3 in front of it, it's not wrong. I don't care. Again, I'm just trying to emphasize the fact that what we care about here is just which direction the arrows are pointing. So the power will help determine that. If it's even, they'll go the same way. If it's odd, they'll go opposite ways. And then whether it's right side up or upside down will determine which side heads which way. So when I go to graph this, all the interesting stuff is happening on the right. So 0, 0, 2, 0, and 4, 0. Okay, so we're going to, let's see, I need to write down my multiplicity. So 0, 0 is the interesting one here because that x is cubed. That has a multiplicity 3. 4, 0 is multiplicity 1, which means just cross right through. 2, 0 is multiplicity 1, so that means cross straight through. Okay, so what does a multiplicity 3 do? When we plug in numbers a little bigger or smaller than 0, this does change signs. If you're cubing a negative number, you'll get a negative number, and if you're cubing a positive number, you'll get a positive number. But what will happen is when we cube these numbers really close to 0, so if you're plugging in 0.1 or 0.01, those numbers actually shrink instead of getting bigger. So we'll get that flat spot that we get on an x cubed or an x to the fifth graph. And again, there's nothing that says which direction this goes. It could be heading up and getting a flat spot or heading down, but it will definitely be a flat spot. So multiplicity 3 should give you a little flat spot right at the 0. That's really important. Sometimes people cross through and then make a flat spot, and the flat spot is at the 0. So at 0, 0, we should have a flat spot. The arrows tell me I'm headed there from negative infinity. So if you check these graphs on your calculator, sometimes the flat spot's kind of subtle. I'll just say for this test, exaggerate them for me. Make sure it's really obvious that there's a flat spot there. So don't make the mistake of kind of just crossing through and having it look linear. The idea here is if I zoom in, I should always be able to see that x cubed shape. There shouldn't be a circle that I can draw with this intercept in the middle of it that doesn't catch something that looks like an x cubed to me. At 2, I'm supposed to cross straight through And at 4, I'm supposed to cross straight through. So there's a rough sketch of the shape of that graph. Okay, last two, I've already got them factored, so we won't have to do the work up front. I just want to make sure I do a couple more examples with powers, make sure you're really clear on what happens. So on this one, our zeros are at 1, 0, at -5/2, 0. If in doubt, do a little bit of scratch work. So if you can't just look at that and spot the -5/2, or if you think you can, but sometimes you get it upside down, go ahead and just do this work to make sure you don't mess up. It's really quick. Set 2x plus 5 equal to 0 and solve. So we can subtract 5 and we can divide by 2. And that's where that's coming from. So if you can see it, great. If not, don't push your luck. I don't want you to make a silly mistake on that because you're trying not to show any work. Okay, so we need to go to -6 and -5/2, so -2.5 and 1, 0. Okay, so those are my intercepts. Global behavior, we want to be a little careful here. The degree of this thing, some people will look and not be careful and they'll say this is third degree, but it's not true. What we really have here is an x minus 1 times x minus 1 times x minus 1 times 2x plus 5 times x plus 6 times x plus 6. So if we imagine multiplying all of those together, we'll have x times x times x times 2x times x times x. So 1, 2, 3, 4, 5, 6 x's. So it's an x to the 6th, and it will be a 2x to the 6th. So the global behavior, again, if you want to write down the 2, you can, but the key part of that is that it's right side up x to the 6th. So these should have arrows going up on both sides. So I'm going to start from positive infinity. When I get down to -6, I have a multiplicity of 2, so I'm not going to cross through, I'm going to bounce off. Signs do not change when we plug in numbers a little smaller and a little bigger than 6 because of that square. -5/2, that doesn't have a power, which means it's a 1. So when we get there, we want to go ahead and cross straight through. And then -1 has a cubed, it's multiplicity 3. So when we get to, I'm sorry, positive 1, I think I said -1. When we get to 1, we're going to make that little flat spot right at the 0. So the inflection point should be right at the 0. It should be concave down as you come to the left, concave up as you come to the right, and then it should just head off. Again, if anything, err on the side of exaggerating those flat spots so it's really clear to me. Sometimes people make them really subtle and I can't quite tell if there's one there or not. Okay, one more. We had a fourth power sneak in on us here. I just wanted to say that if the powers get higher, it's really all about even and odd more than anything. So a fourth power is still going to be a bounce. A sixth power would still be a bounce. A fifth power would still be a flat spot. A seventh power would still be a flat spot. So there's basically the first, second, and third power shapes that you have to worry about. First power is unique. That's the only one that crosses straight through without making any extra bendiness. Any even power bigger than that is going to make a bounce, and any odd power bigger than 1 is going to make a flat spot. So let's see, my zeros are going to be at -20, at, oh, I skipped one, at +4, so let's say right about here, and then what is this one, at +7/5. Oh, I picked interesting numbers here. Okay, so at +7/5, that's a little bit bigger than 1, so right around here. We don't know why I picked this combination of numbers, but we'll go for it. So at -20, I have a multiplicity of 4, which means I'll bounce. Oh, and I need my global behavior. Okay, so if I multiply a -x times 4x's times 5x times 5x times 5x, 3 5x's. So I have a -x, and then I have an x to the 4th that I'll get out of this mess, and I have a 5x to the 3rd that I'll get out of this mess. So I'm going to get a -125 x to the 4, 5, 6, 7, 8. So upside down parabola type behavior. So I'm going to start from -infinity. And again, if I'm asking you global behavior, I don't care if you write the 125 or not. I do care about the x to the 8th and the negative. At negative 20, I'm going to bounce. It's an even power, which means the y values won't change signs. And then I'm going to head down for a while. And then at, where am I? 5, at 7/5, I'm going to have a flat spot. And then I better turn around fairly quickly because at 4, I have to cross straight through. Okay, so a good thing to point out here, this is looking kind of straight, is this is not counting as some sort of bounce at the intercept. I can draw a circle around this, and if I hide everything else from myself, circle centered around my intercept, it looks like it's a straight line, and that's what's key. And the same thing right here. I can draw a circle around it where even if I hide everything, I can still see that kind of x cubed subtly shape, that there's a change in bend there. And here I can see that x squared shape. Okay, so I think that's it for this video. Thanks for watching.